we were talking about random variables and random vectors. We talked about expectation of a random, recall the expectation of a random variable, its connection to the law of large numbers. The expectation of a random vector. A random vector is just a collection of random variables compiled into a vector, and the expectation is just what we'd expect. So you apply the expectation operator individually to each coordinate, and so you get a deterministic vector. Each coordinate, basically the I coordinate, is going to be the expectation of the I coordinate of Y. And there's this property of expectation. Expectation is linear, which means that it passes through linear operations. So it passes through summation, it passes through a scalar multiplication. And so in general, if I have a linear combination of a bunch of variables with coefficients that are deterministic, what would happen is I would get the linear combination of the expectations with the same coefficients. So, so this led to this idea that if you want to compute the expectation of the matrix times Y, we can basically take out A, and then an extension would be when we have a multiplication of multiple matrices. Let's say G matrices, B and C are deterministic constants, and A is a random matrix. The expectation passes through, and we did an example of this. So there's an important property that we'll use quite often. So it's good to get comfortable with this property. And so now we're going to use it actually in this lecture. And then we talked about the variance. The variance is a measure of spread, how spread out you're around the mean, or the variable is around the mean. And because of the way it's defined, it's invariant to shift. So it's basically the second moment of the centered version of the random variable. Okay, so we have a random variable which is x, and then if I center it, I will get. Sorry, this doesn't seem to properly work. Okay, if I center it, I would get x tilde, and this x tilde is x minus mu, and so the expectation of x tilde is going to be x squared is going to be the variance, and then the idea of covariance was how linearly they're dependent, and so this is the definition of the covariance, and so you can see again. Easy to define based on the centered versions of that random variable. So x1 minus mu1. Mu1 is the expectation of x1, and this is the expectation of x2. And so this is related to how these two random variables vary together. So if they vary together very close to a line, like the xy line in the xy plane, this would be positive if they vary like close to a line, but in the opposite direction, like the 45-degree line, but in the other direction. This would be very negative, and if there's no linear relation sort of scattered basically around, not around the line, this would be close to 0. But how close it is to 0 or how big it is depends also on the variance. So usually you divide it by the square root of the variances of the two variables involved. This is called the correlation coefficient. And this is always guaranteed to be in -1 and 1. Okay, so it's a normalized measure of linear dependence. And one particular property is that if x1 is independent of x2, then the covariance is going to be 0. Because anyone knows why? If x1 is independent of x2. Yes.
Covariance is like how related they are, and they're not related. They're independent, so that means the covariance has to be 0.
Yeah, so that's the intuitive answer, but like formal proof, how do you formally prove it? Yes.
Yeah, so covariance also it's x1 minus. Okay, the other way I knew it's expectation of xy times the x minus the expectation of x times the expectation of y, and if they're independent, then expectation of xy is the same as expectation of x and expectation of y.
Yeah, so this can be written also as this. This is also like expectation of x2. So if they're independent, what would happen?
The first term becomes expectation of x1 is expectation of x2 by.
So expectation of x1, x2 would be expectation of x1, expectation of x2, right? And so the covariance would be this guy minus the expectation of x1 times expectation of x2, but in this case, this guy is also equal to that, so this is going to be 0. Same thing here. What I did above is similar. So these are all alternative expressions. So this is the covariance. Usually this is how it's defined. If you expand it, you'd get this expression. And if you call this x1 tilde, this is the centered version of x1. If you call this x2 tilde, centered version of x2, then you can write it that way. What I did last time is you can also write covariance as this, but when x1 and x2 are independent, any function of x1, deterministic function of x1, and any deterministic function of x2, if you apply, basically this is going to be more general. So let's try this. So if x1 is independent of x2, then this is true. Expectation of f of x1 times g of x2 is going to be equal to the expectation of f of x1 times the expectation of f of g of x2. So you can basically decompose the expectation of product into the product of expectation.
I'm here.
Okay.
Sorry, I couldn't find anything like that in home.
So x1 times expectation of g of x2. And then we do this a little bit. Times the expectation of. So if you apply it with f of x1 being x1 minus mu1, and f of x2 being x2 minus mu2, these are deterministic functions. And so this would be the covariance by definition. And this would be 0 because you apply expectation to this and it moves inside. So both of the terms are going to be 0. So that's what I'm doing here. So the covariance would be this, but then it decomposes into that and it would be 0. Sounds good. So that's the covariance. So what is a covariance matrix? Covariance matrix is a matrix that contains the variances on the diagonal and the pairwise covariances on the off-diagonal elements. So the covariance of the covariance matrix of a vector, this is how I usually write it. Some people write it as var of this guy because it looks like a variance, like a multivariate variance. So this is going to be an n by n matrix if they're n coordinates. And the ijth entry is going to be covariance of xi, xj. And the ith entry is going to be similarly covariance of xi and xi. And it's not hard to see that the covariance of xi and xi is just the variance of xi. So the diagonal is going to be x1 up to xn. Off diagonal is going to be covariance of xi, xj. Okay, so that's how far we went last time. Any questions? Okay, so these are the definitions. They're based on the y now. So the covariance matrix of y is an n by n matrix. The ij entry is the covariance of yi, yj. This is the expansion of the covariance, just the definition. So there's an alternative expression for the covariance. You've seen it. This is the alternative expression. And these statements would translate into corresponding matrix expressions. Before giving you that, we observe that this covariance matrix has a bunch of properties. That's called sigma. So covariance of y is sigma. This is an n by n matrix. It's going to be symmetric. It's going to be a symmetric matrix, which means that sigma is equal to sigma transpose. So why it's going to be symmetric? Yes.
Because the covariance of x1, x2 is the same as covariance of x.
Yeah, so covariance of x1, or let's say xi, xj in general, is equal to the covariance of xj, xi. So that's the definition of symmetry for a matrix if the ij entry is the same as the jth entry. And you can also see it's like equivalent to saying that the transpose of a matrix is equal to itself. If the elements of the vector y, they're pairwise uncorrelated, so pairwise uncorrelated means covariance of yi, yj is equal to 0 if I is not equal to j. So every off-diagonal element is going to be 0 by definition. So the covariance matrix will be diagonal. So you only have the variances on the diagonal. This is sort of almost the definition. If you let the expectation of y, this is a vector, be mu, now mu is going to be an n-dimensional vector itself, right? So mu is going to be mu1 to mu n. So each element is going to be the expectation of the corresponding entry of y. Then I can, so this expression, which holds for individual, the pair of random variables, this can be expanded to this expression for the entire covariance matrix. Okay, so you take y minus mu. This is an n by 1 matrix, and then you transpose it. This is going to be 1 by n. So I have this y minus mu, and then I transpose it. So you get y minus mu transpose. And so n by 1, 1 by n. And if you multiply it, you would get n by n matrix. So this is a random matrix. And if you take the expectation of it, that would be the covariance matrix. Another way of writing it in a compact form is called this y tilde, the way we did for the usual random variables. This is the centered version. This is going to be y tilde transpose. So this expression is exactly the same as what I wrote down there. So the expectation of y tilde transpose. So that's simpler. So let's see if someone can argue why this is the case. Can you tell me what the ij entry of this would be? will be the ith row. I don't have an expectation, but how do you multiply these two matrices? So then find the ith row of this matrix. What would you do? You take the ith row of this, multiply by the other. So if you want to just think about it, the first entry multiplied by the first entry would be the 1 entry of the other. The first entry times the second one would be 1 2 entry. Okay, so in general, the ijth entry of this matrix is y tilde I, y tilde j. So if you think about how matrix multiplication works, that's how it works. Okay. If you want to multiply, like the first row gets multiplied by the first column, you get 1 entry. The first row gets multiplied by the second column, you get this times that, you get the 1 2 entry, and so on. Because that's like that, the ij entry is like when you take the expectation of this matrix, applied coordinate-wise, the ij entry of the expectation will be the expectation of this guy. And this is the covariance of ij. So if you think about it, this is really just the consequence of the way the matrix multiplication works. But this is nicely connected to this expression that we had before. So instead of writing something like that, now you write, for example, x1 tilde transpose. And then another expression for this is if I expand this expression, I get a similar expression for the covariance matrix, which corresponds to the second representation of the covariance of two random variables. You get the expectation of y transpose minus mu transpose. And just expand things, and this is another expression for the covariance matrix. So these are just matrix versions of the two expressions or three expressions that we had for the covariance of two random variables. Now they're for a covariance matrix. Okay. Sounds good. Questions? So these expressions, especially this one, compact version, is very helpful to drive properties of covariance matrices. The last property is that the covariance matrix is invariant to shift, similar to the variance. The easiest way to see is that because we are defining it, or is based on the centered version of the random vector, and if I shift the random vector, the centered version does not change because I always subtract the mean. If I shift the random variable by a constant amount, so let's say I add b to y, b is, so this is n by 1, this is n by 1, and this is deterministic. When I try to compute the covariance, so this I have to compute the centered version of this by subtracting the mean, its mean from itself. So the mean of this would be expectation of y plus b. When I subtract, the b's cancel out, so you get y minus expectation of y. So the centered version of this vector is the same as the centered version of y, so the covariance would be the same. The covariance matrix would be the same. So covariance matrix is shift invariant, which is very useful. The other thing is that, so if I look at, for example, alpha times y plus b, this is in R. This is going to be first equal to alpha y because I can drop b, and then I can pull out alpha, but alpha scalar comes out squared. So this looks like a variance basically. So you get alpha squared times covariance of y. This also follows easily. The centered version of this is going to be alpha times y tilde. And so when you plug it in here, you get two alphas multiplied by each other, and it comes out to the alpha squared. So everything follows from this formula. Okay, but it's good to have this in mind. Okay, covariance is shift invariant, and also this is how it behaves under scaling. Sounds good? Sort of. Okay, so I want to now discuss the very important property, which is how covariances change under linear transformations. Okay, so we had, for example, random vector y, you multiply it by a matrix A, so you get AY. We know how to deal with the expectation. So if I have A is an m by n matrix, I have y, which is random. If I form AY, I know what the expectation is. Or I know like a formula, nice formula, how to compute it based on the expectation of y. And this lemma gives you how the covariance behaves. So this is the same random variable. The covariance of AY would be A times the covariance of y times A transpose. It's a little bit more complicated than expectations. The covariance is not, like the covariance operator is not, like as a matrix, doesn't act linearly, like variance or square. So you get A, covariance of y A transpose. So this makes sense because this is m by n by n, this is going to be n by n. So the dimensions match, you can multiply things out. And this gives you an easy formula, sort of, calculate the covariance of the linear transformation of y. Is this statement clear? Right. Let's see how do you, okay, I can use this nice tool. How do we prove it? Anyone can help me prove this? I want to use this formula. Let me give you a hint. So let u be AY. U tilde be the centered version of u, so u minus the expectation of u. And y tilde be y minus the expectation of y. Okay. So by definition, so you want to compute the covariance of u. Okay. And this is going to be equal to the expectation of u tilde transpose. Now, can anyone tell me an expression for u tilde? So can I relate u tilde to y tilde? Yeah. Okay, great. So how do we argue for that? Why is that?
Because u is AY, so if you set your both in the matrix multiplication, still that is still equal.
If I do, sorry, what?
So then you can do the same thing on the tilde, like you can change it to u tilde and y tilde, you can still multiply the A, still be.
Yeah, but that's the claim. Can you prove it? You're just putting tildes on both.
Right, because they're both centered, so.
Okay, I mean, it's sort of obvious, but there is a bit of argument here. So let's say if I apply A to u tilde, right? So I get A times u minus sorry. So I get A times and no, okay. This is already, so u tilde is u minus the expectation of u, right? So u is AY, and the expectation of u is the expectation of AY. So this is by definition of u. That's how we define u. Right. So now, what is the argument here? This is going to be AY. This is going to be Yes.
That's just y. You can factor the a out because linear here.
Yes, linear to
Then you can
expectation.
do y minus expectation of y is 1.
Yeah, so now I can factor, so this a comes out, then I can take one a out, factor one a out, I get something like that. And so you get a times y tilde. Okay, so this is proof that this guy so this is equal to a y tilde. Okay, so there is a bit of argument here, and that follows by the linearity of expectation. So if you have u equal ay, if you center u, it's gonna have the same relation to the center version of y. So u tilde would be a times y tilde. But there's like this one line argument there. Okay, that's the first step. Sounds good. This uses the previous property of linearity or expectation that we established. Questions, comments? So now what is the next step? So I have this property that I can express u tilde in terms of y tilde. So how should we proceed? Expectation u tilde transpose. I'm going to proceed myself, a y tilde transpose. Now you tell me what the next step is. I'm just going to plug in u tilde there. Yes.
Use the property of transpose. And then
Sorry, can you
use
say?
the property of transpose.
Okay.
And then you kind of distribute transpose. So like the order of the y tilde a changes. but you
Great.
take out the transpose one.
So we're going to use the property of transpose. When you transpose a product of two matrices, the order changes, and you can put transpose on each one. So you get y tilde transpose, a transpose. Okay, so this is using the fact that if I have like BC transpose, I get C transpose, B transpose. Okay, this is how you distribute the transpose. So I get that. So next step. I can put parentheses around it, but there's no need because matrix multiplication is sort of, you can rearrange parentheses any way you want. So I'm just gonna write it without parentheses first. So it doesn't matter in which order. So that order matters, but in what sequence you multiply doesn't matter. If I multiply y tilde transpose first, and then by this, and then this, or if I multiply this by that first, and then multiply by this. So where you put parentheses, where you start multiplication doesn't matter. The order matters, like so I can't switch them around, but I can multiply them any way I want. So I used to multiply them like this. First, multiply these two. Okay, let me maybe do that. So the way we did it is like multiply this first and then that. Now I'm gonna remove parentheses and put parentheses elsewhere. So I'm gonna do something like expectation of A, and then I'm gonna put parentheses inside here. First multiply these two parts and then this. This is still valid. Because I haven't changed the order, I just remove parentheses, put parentheses here, which means that I first multiply these, then you can also put parentheses also, but it doesn't matter. So you don't necessarily need parentheses. But what I'm saying here is just first multiply this part, and then you get three matrices, you can multiply them in order you want. So the reason why I did this, can anyone tell me why? Yeah.
Since the expectation of the next two.
Yes, so you're going to use that property again, linear expectation. These two matrices are constant. This is random, so the expectation is going to move past these guys inside, and so I get expectation of So A comes out from this side, A transpose comes from the other side, and I get expectation of y tilde transpose here. And this happens to be by definition the covariance of y. Okay, so that's the thing that we wanted to prove. That's the proof. So we use the linearity of expectation twice, once to establish this idea, or this identity u tilde is equal to ay tilde, and then the next we use it here, going from this step to that step. Sounds good. Questions? So let's go back to an example here. Do you have an example? Yeah, okay. Yeah, okay, so I don't have a good example there. I have a couple of examples here, but let's do an example not related to the slides. So let's say y is y1, y2. y1 and y2 are normal 0, 1, IID. Right, suppose I want to compute the covariance of y1 plus y2 and let's say 2y1 minus y2. It's minus 3y2. Let's see. Okay. So there are a couple of ways that I can proceed. So one way I'm going to use this lemma. The other way is from direct calculation. So if you don't know that lemma, can you compute this covariance? Yes.
You can set up the whole A.
Let's forget about this. Let's say if you don't know
Yeah.
about it. Yes. Do you know it from previous courses how to calculate something like that?
Find the distribution of each of the two separate.
You find the distribution. Sorry. You can find the distribution of the two separate one, you mean?
Like you can find distribution of y1 plus y2.
Okay.
And then from there you take that.
So if you want to do that, you have to find the joint distribution, not the distribution of each one separately. So you need to find the joint distribution of this and that. Right, because it's a property of the joint distribution, not individual. Is there an easier way in this case? Do I have to compute the joint distribution? That's definitely doable, but a lot of work. So you have to be able to calculate, like you have to find the PDF of y, and then know how the PDF transforms under this transformation, and then do the integration for the expectation. So we had something like this in homework 1. We haven't yet talked about this, but you guys did it anyways. So how did you do it? Just did it, yes.
Well, I did it with that.
Okay, with that property. Okay. Good. Okay, so you look at the head. You look ahead. So we can do it. We'll do it that way. But there is a property of covariance matrix, the covariance operator. So this is like a single number. So this is might be a little bit confusing, but I use covariance on a matrix. This is going to be the covariance matrix But when I use it on two random variables, let's say u1 and u2, these are single random variables. This means just the covariance between them. Okay, so let's be clear. Here we are using that notation. So the covariance operator acts on two random variables. So the covariance operator that acts on two random variables, this is a bilinear operator. So that's the key that I want to emphasize. A bilinear operator. Two notations. So this is covariance matrix of vector y. This is covariance of two scalar variables. Let's not confuse them. So the covariance is a bilinear operator. So I mentioned a bilinear operator in one of the previous lectures. Anyone remembers? What was a bilinear operator? What it means to be a bilinear operator? Yes.
Like the covariance of y1 plus y2 equals like the covariance of y1 plus the covariance of y2.
Covariance of y1 plus y2. Can you say it again?
Like that's equal to like the covariance of y1.
So it has two arguments, so you need to provide another argument.
The variance of y1.
No, let's say you want to compute the covariance of. So let me go back. So we'll get to that. But what is the other like bilinear operator that I mentioned? Just like a comment at the bottom of a slide, like exercise involving this identity. You remember? Oh, good. Yes. So I mentioned that the inner product is a bilinear operator. So what it means is that I can sort of write this as a minus b, and then I can distribute as if I'm doing just the usual product. So you get a and a minus b plus minus b and then minus a minus b. So think of this as like fixed. So I can distribute it to the two side and then distribute it further. So a minus ab minus ba plus bb, something like that. Okay. And these two are because of the symmetry, this is going to be AB, so you get AA minus 2AB plus BB, you get A squared. This is just AB, that's the same thing. B squared. So bilinearity means I'm linear in each coordinate, so I can distribute. So if I have like covariance, this is the same thing. So if I have covariance of, so inner product is bilinear, is another bilinear operator. Just inside, like a detour. So covariance of, let's say y, or let's say u1 plus u2, and u3 would be covariance of u1 u3 plus covariance of u2 u3. Okay, just expand the first thing out. And the same goes for the other one. So it's linear in the first coordinate, linear in the other coordinate. So that's why it's called bilinear. So if I have like covariance of u1 plus u2 and on the other side u3 and u4, you get 4 terms. So the easiest way to understand like how the bilinear operator works is if I give you like two numbers, so a and b are in reals. Let's say x and y are reals. Okay, like u and v are in R. If I tell you like to multiply 2u minus 1 times 3v plus u, right? Maybe V here. So this is a bilinear operation. It's a usual product. So the way you do it, you just distribute everything. So you get 6 UV, like the first this multiplied by that, and then 2 plus 2 U2, like this multiplied by that, minus 3V squared minus VU. That's how you do it, right? So you get 4 terms, just distribute this multiplied. So each one gets multiplied by the other one. Okay. So the same goes if I have like covariance of 2U minus V and 3V plus U. So you can just ignore the covariance, assume that it's just product. So you get 2, or just think of this as doing this. Do this for yourself, and then just replace these with covariances. So you get 6 covariance of UV plus 2 covariance of UU minus 3 covariance of VV minus, if you did the product correctly, covariance of VU. So this would be variance of V. This would be variance of U. Okay, so you can do bilinear, because it's a bilinear operation, it behaves like just multiplying things out. Okay, so you don't have to think too much. What happens is that I take this as the first, like a single variable, I can expand this part because it's linear. And then once I do that, each of those terms I can expand. So it gets 4 terms and it just behaves like that. So behaves like usual product. Okay, so that's what I wanted to first mention. So if I want to do this, let's see if you guys can. Now, can anyone tell me, like, how can I write expression that I can write for this? Just using this technique, bilinearity covariance. Yes,
Just the way you just did that one.
can you do it?
Yeah, you get 2 variants of y1
2 variants of y1.
plus
So this times that basically.
minus 3 variants of y2 when you multiply the last two.
The last two, so you're doing this, okay, minus 3 variants of y2.
You get minus 1 variance of the other ones because you have a plus 2 and a minus 3.
This times that, so minus
Minus 3 and the other
covariance
one
y1, y2, and then you get this times that, right? It's plus 2 covariance of y2, y1.
those traits are the same, so you can combine.
They're the same, so because of the symmetry, right? So this would be equal to covariance of y1, y2. So I can now combine. I get, for example, 2 variance of y1 minus 3 variance of y2, right? Minus variance of y1, y2. Is that correct? And if you have y1 and y2 are IID normal, so y1, y2 are IID normal 0, 1, what would I get? What is the variance of y1? 2 times 1 minus 3 times 1 minus 0, because they're independent. And so if they're independent, they're going to be autocorrelated. We talked about that. So, it's going to so you get -1. Okay. The covariance could be positive or negative. It's fine if you haven't done any mistake. Okay. So that's a direct way of doing it. Questions? So now let's do it by the approach using A. So how do we do that using this result? I want to calculate this. So maybe you can now tell me how to define A and move forward. So I want basically write this. I want to write this joint, like this is a new vector. I want to write it as a matrix of y1, y2. That's what we want to do. Then I can compute the covariance matrix of this. And so the off-diagonal elements would be the covariance of the two coordinates. The diagonal elements would be the variances. So I gain more information that I need, but I get what I need as well. So how do I write this as a matrix multiplied by that?
First rows y1 and rows 2.
Okay, good. So this is the A matrix, right? So now the covariance of y1 plus y2 to y1 minus 3y2. This is going to be A covariance of y1, y2, A transpose. Okay, so I get 1, 1, 2, negative 3, and then transpose of this, which is 1, 1, 2, negative 3. So what is the covariance matrix of y1, y2? 1, 0, 0, 1. Why? Why?
The diagonal is the variance.
Diagonal of the variance there.
Covariance.
Covariance is 0, right? Okay, good. So this simplifies because the identity sort of goes away in a sense. I multiply this part, I get that. Let's multiply the other one. So I guess you know how to multiply. So this is going to be 2, right? And then 2 minus 3 would be minus 1, and then what will be the last one? 9 plus 4. What is this one? Minus. Is it going to be 4 plus 9?
Oh,
13. Okay. Okay, so the last one has a lot. So this is going to be the variance of this guy. This is going to be the variance of this is pretty large. And the covariance is going to be negative 1. So the covariance matches what we did before. Okay. So you decide which one is easier. So this gives you more information. If you just want the covariance of these two, this might be faster, depending on the situation. Good. Okay, so we're going to use this a lot in this course. So it's good to get comfortable with it. And let's move on. Any questions? So I have a bunch of other examples. These are symbolic examples. It's good to go through. This is another one I did using the two approaches. You can go over yourself as an exercise. The next one that I want to talk about is this proposition. So any covariance matrix is positive semi-definite. Okay. So this is an interesting result. And if you calculate the covariance matrix, it's not positive semi-definite. You did something wrong because it's going to be always positive semi-definite. So what is a positive semi-definite matrix? Yes. So it's a matrix whose eigenvalues are greater than or equal to 0. This is a good statement, but usually is not the definition. It's like a property that you prove, right? It's a characterization, like equivalent characterization of PSD, positive semi-definite. Yes.
All the entries in the matrix are good.
All the entries in the matrix are greater than or equal to 0. Is that correct? This is a great definition, which is not correct. So like the great example of what a PSD matrix is not. Okay. So that's a non-negative matrix, but I told you that the covariance matrix is going to be always positive semi. So this is a positive semi-definite matrix. We'll prove that. So it can have non-negative entries. So it's like a non-negative number, but the entries can have. So good. Let's write it down. So a PSD matrix has all entries non-negative. That's what it is. Write it down because it's important. Where is it? PSD matrix is a matrix whose elements are all non-negative. This is false. Okay. A matrix whose just say a symmetric matrix. This is going to be always a symmetric matrix. Symmetric matrix whose eigenvalues are all non-negative. Is this true? False. This is true. Okay, so what is the other, the way that we actually defined it? Yes.
Would it just be all diagonal entries? Would be
A symmetric matrix whose diagonal entries are all non-negative. What do you guys think? This is true, but I'm going to write it as partially true. Why partially true? Yes.
Because it's like the definition, because variance is always positive.
We haven't proven like the covariance matrix is positive, but positive semi-definitely is general more like concept separate from covariance. It is true, but
A matrix can have all positive diagonal entries without.
right. So it's not enough. So necessary, but not sufficient. So this is both necessary and sufficient. So this is like equivalent characterization eigenvalues, but diagonals are always going to be non-negative if it's PSD, but you could have a matrix whose diagonals are non-negative, but it's not PSD. So these are good. So the next one, can anyone tell me what the characterization I'm looking for, which is the definition, the way that people define it.
Like the inner product between X and AX, where A is the spectral decomposition of X.
Okay, that got complicated. So let's matrix. So the inner product such that the inner product between X
And AX.
so X is what?
X is a matrix.
This is close. So okay, let's go with what you say. X is a matrix, but then there is no inner product between A and AX. So this would both would be matrices. So inner products are usually between vectors. Right. Is there something that you're looking for? Like matrix spectral decomposition? I don't know. So this makes sense if X is a vector. This, if it's a matrix, you have to do something else with these two. We can leave it at that. Think about it if there is a characterization. There are many characterization of positive semi-definites, but yeah.
Is a symmetric matrix positive semi-definite if you can find a vector x where its components are greater or equal to 0, and you can multiply A with x and x transpose to get
That's close. So these are close characterizations, but you don't need that the eigenvalue, like the vector to be non-negative. So this, or let's say x transpose AX, this has to be non-negative for all x in reals, like for all vectors. So the inner product of x and AX has to be non-negative. Yes.
Does it have to be symmetric?
Matrix A has to be symmetric. Yes. Yes. So this is like this positive semi-definite is about symmetric matrix. If it's not symmetric, this doesn't make sense because let's say if this was m by n, this would be n by 1, but then this is n by 1, like 1 by n, sorry.
Could it still be n by n but not symmetric?
Good, yes, okay. So n by n, but not symmetric. Very good question. Can you have a like n by n matrix non-symmetric and satisfy this?
Still take the inner product. But the inner product will-
You can still take the inner product. So let's see. You have like n by n non-symmetric, and then you can have x transpose AX be non-negative. There are matrices like that. Are there matrices like that? So I can have like 1, 0, 0, but this is symmetric. Yeah, so the question is that is it possible to have
Then you do like 1, 2, 3, 4 for like
1, 2, 3, 4?
let x be 5, 6.
So you just want to like give. So this is not saying just for one x, it has to hold for all x,
Right. Okay.
right? It's not enough to give an example where,
Right. Okay. So then can you just do that's what it's doing to that? Or does that?
so you want to do this for this general. So it's a good question. So let me think about it. Whether it's usually defined for symmetric matrices, but so you can at least form something like that. And sometimes it's called a quadratic form. Quadratic form in X, we'll see. So there's a quadratic form in X with matrix A defining it. So this saying that the quadratic forms in the matrix are not negative. So whether that can hold for a non-symmetric matrix, that's a good question. I want to say can't hold, but you guys can think about it. Can something like this hold for a square non-symmetric matrix for all x? Let me get back to you on this. I want to say it can't hold, so you have to like be symmetric. So you can impose symmetry from the start, or you can say this is the definition and it forces symmetry itself. So there is no non-symmetric matrix. So that's like a genuine math problem. So you have to prove it's not obvious to me, but my guess is that if I recall correctly, you can prove it that it can't hold. But let's get back to that. It's a good question. But for us, like majority of mathematics, PSD matrices are symmetric, either by definition or you can drop it from the definition and then say this forces it. But that's the definition. Okay, so this has to hold for all x. There are other characterizations. Okay, just going to mention a matrix that can be written, symmetric matrix that can be written as like A equal R transpose. So if you can write it as the product of a matrix times its transpose, or vice versa, I mean, it's equivalent, like, or like, say, R transpose R. If you can write it like this, here you can just replace R with R transpose. So if you can write it like that, you posit semi-definite. It's very easy to show from this definition. So if you have something like that, then this would hold. Write this down, and then you can see why that is. There are probably other characterizations. There are other characterizations in terms of the determinants. So all the principal matrices have non-negative determinants. So characterization in terms of determinants. But this is the definition. And this is the one that's going to be very useful, the eigenvalue characterization. So this, I say these two are, sorry, not this. This is the definition. Okay. Okay. So we're going to use this definition. Such that symmetric matrix such that this whole is positive semi-definite. Okay, so let's try to prove that the covariance is positive semi-definite. So how do we prove that? So anyone knows how to prove this? Using this definition. So let's do it with A instead of X. So we have proof, right? I want to show that, let's say, sigma is covariance of Y, which is also expectation of Y tilde transpose. Pick A in Rn. I want to show that A transpose sigma A is non-negative. That's what we have to show. Want to show A transpose sigma A. So the trick is to note that this is the variance of a particular random variable, and because variances are non-negative, this has to be non-negative. So that's the trick, the proof. So anyone knows what this is the variance of? So you imagine this result that we had. Okay, so here we have A sigma, so A transpose sigma A, right? So you can reconstruct it back. So what is this side? If this side is A transpose sigma A. That will be the covariance of A transpose Y, right? So if I write covariance A transpose Y, that will be equal to A sigma A transpose, right? But A transpose Y is a scalar, a single number, so the covariance matrix of A transpose Y is just its variance, right? So this is saying this is true, but this is just the variance of A transpose Y. Okay, so this property, if you apply it with capital A being A transpose, this shows that variance of A transpose Y is equal to a covariance of Y, basically sigma A, it's covariance of Y. And because the variance is not negative, this has to be non-negative for all A. Okay. Yes.
But why is that variance of A transpose Y? Because usually covariance is the other thing.
Yes, so this is going to be so A transpose sigma A is going to be covariance of A transpose Y, but Y can I write it as the variance of A transpose Y? Why? Just mention this. So A is n by 1, Y is 1 by n. So what is the dimension of A transpose Y?
Scalar.
Scalar. So what is the covariance matrix of a scalar? Yes. Right, it's just a 1 by 1 matrix. A 1 by 1 matrix, the covariance matrix is just its variance. Right? So we reduce this to that. And this is non-negative. So it's a one-line proof from that property, but it's interesting. So first, it tells you that these things that appear in the positive semi-definite characterization definition, these are variants. Like if you apply it to its covariance matrix, this definition, these are variances of linear combinations of the elements of Y. So it has this meaning. And so it immediately shows that the covariance matrix has to be positive semi-definite because these so-called quadratic forms are variances of linear combinations of the elements of Y. Sounds good? So every covariance matrix has to be positive semi-definite because this is going to be always true because this is the variance of something and the variance of something is not negative. So the opposite is also true, but we're not going to show. Every positive semi-definite matrix is the covariance of some random vector. Okay, so there is a one-to-one correspondence. So you can think of positive semi-definite matrices and covariance matrices as sort of the same class of matrices. What we showed is that if it's covariant, if a covariance matrix is positive semi-definite, the other thing that the other direction is basically when we talk about Gaussian variables, it's not proof, but for every positive semi-definite matrix, there is a multivariate Gaussian distribution that has that covariance matrix. That's the result. So there's at least one distribution that gives you that covariance matrix. There are many more distributions, but at least one random variable, at least one is the Gaussian random vector that produces that covariance. So we're almost out of time. So this last one is just optional. And I'm just going to mention, this is about the case where so we had positive semi-definiteness and we had positive definiteness, remember? So if this is strictly bigger than 0, if x is non-zero, then we call this positive definite. Okay, so if the inequality is strict for all non-zero x, because for if x is 0, this is always going to be 0, we can't change that. But if x is non-zero, this inequality is strict for all such x, for all non-zero x, then this is a positive definite matrix. You drop the semi. And the equivalent characterization of the eigenvalues are strictly positive. But in that case, if it is positive definite, it means that these variances of these linear combinations are all strictly positive. It is like genuine PSD, which means that there is like, if it happens that it's not positive, it's positive semi-definite, but not positive definite, it means that there is one A at least such that this variance is 0. There is one A such that this is 0. And so there is non-zero A. So in the pathological case, there is non-zero A such that this is 0, this covariance, which means that the variance of A transpose Y would be 0. And so anyone knows what happens if a random variable has variance 0? Yes.
It's always the same thing.
It's constant, yes. It's always, so we probably want A transpose Y would be constant. And so in this pathological case, Y1 and like the elements of Y satisfy a linear constraint almost always. So it's like, for example, I would have A could be like 1 minus 1 transpose times Y1. Y2 is constant. This means that Y1 minus Y2 is constant. So the difference is going to be always the same thing. So this means that the random vector lies in a lower dimensional subspace of the original space. So it lies on, for example, in this case, in the R2 plane, this is going to be some sort of a line. So if you plot draw things from this distribution, they're going to be always around a line. So when you draw from this, it's not going to be scattered around the place because you know that this random vector is always going to satisfy this constant. So these are like distributions that are lower dimensional in nature. For us, usually, so this is also equivalent to this covariance being singular. Covariance is not invertible, or one of the eigenvalues is 0. If all the eigenvalues are positive, this can't happen. The covariance can be inverted, so the covariance is non-singular. So if the covariance is singular, which means that one of the eigenvalues is 0, which means that this one of like there is a direction such that this holds. That direction actually corresponds to the eigenvector that corresponds to the 0 eigenvalue. And you have a constraint like this and distribution that collapses to a lower dimensional subspace. Just a side note, we are out of time, but there's this last slide. Maybe next time when we come back and talk about this, you can decorrelate. You can apply a transformation to a random vector that makes this covariance identity. Okay, and that covariance, that transformation is related to the inverse of the square root of the matrix, the covariance matrix. Okay, and with that, we're going to move on to the next topic. Thank you.